Welcome to The Explainer. Today, we're diving into something really cool at the heart of modern AI, knowledge distillation. We're going to break down the magic trick of how engineers take these absolutely massive AI brains and shrink them down so they're small and fast enough to run right on your phone. Okay, so let's just jump right in. The most powerful AI models out there, the ones that are creating incredible art or writing code, they're huge. They live on these massive server farms, definitely not in your everyday devices. So the big question is, how do you bridge that gap? The models you hear about in the news have billions, sometimes even trillions of parameters. And all those parameters make them incredibly smart, for sure, but also incredibly slow and power hungry. They're just too big, too expensive to be practical for widespread use on something like your laptop or, your smartphone. But back in 2015, a team led by AI pioneer Geoffrey Hinton came up with this truly elegant solution. It was all centered on a brilliant, kind of mysterious idea he called dark knowledge. The concept is called knowledge distillation, and it's actually built on a really simple analogy that makes a ton of sense. You take a huge, powerful teacher model, and you use it to train a much smaller, more nimble student model. The whole point is to get the student to perform nearly as well as the teacher, but at a tiny fraction of the size and cost. Now, here's the real genius insight. A big teacher model doesn't just know the right answer. It also knows why other answers are wrong, and even how wrong they are. This really nuanced understanding, it's all hidden in the probabilities it assigns to the wrong answers. And that's the dark knowledge. So think about it this way. Standard training just uses what we call hard labels. It tells the model, hey, the answer is 2, period. But a teacher model gives us soft targets. As you can see here, it might be 95% sure it's a 2, but it also tells us there's a small chance it could be a 3 or a 7. Now that is a much, much richer signal for the student to learn from. So to make sure the student can actually see all this hidden info, researchers use this clever mathematical trick. They apply something called a temperature parameter, which basically softens the teacher's predictions. It's like turning up the volume on those subtle hints, making all that dark knowledge way more visible and easier to learn. But, the field evolved pretty quickly. Researchers started to realize that knowledge is way more than just the final answer. The teacher's internal thought process, the how it gets to the answer, is just as valuable as the final what. And this led people to create a kind of taxonomy, breaking down knowledge into 3 main types you can distill. You can copy the final answer, which is the what, you can copy the thought process, which is the how, or you can even copy the teacher's entire mental map of how the data is structured. So first up is response-based knowledge. This is Hinton's original idea. The student just tries to mimic the final output probabilities of the teacher. It's super simple and really flexible. The student and teacher can be totally different, but it does kind of miss out on that rich internal reasoning, the why. Feature-based distillation, though, goes a layer deeper. Here, the student tries to copy the patterns from the teacher's internal layers. It's almost like the teacher is giving the student hints along the way, teaching it not just the answer, but how to find the important features in the data. Basically, teaching it where to look. And finally, we get to the most abstract form, relation-based distillation. This one doesn't focus on individual answers or features. Nope. Instead, the student learns to understand the relationships between different data points, just like the teacher does. It's all about capturing the entire geometric map of knowledge that exists inside the teacher's brain. So once these foundational ideas were out there, the floodgates just opened. It sparked this absolute explosion of creativity, leading to a whole suite of new, more powerful, and sometimes kind of mind-bending distillation methods. First up is self-distillation, which is a fascinating paradox. In this method, a single network literally teaches itself. The deeper, more knowledgeable layers of the model actually provide guidance for the shallower layers, which forces the whole network to become more consistent and robust. You don't even need an external teacher. Then we have multi-teacher distillation. Why learn from just one expert when you can learn from a whole committee of them? Here, a single student model learns from an entire group of different teacher models, combining all their unique strengths to, hopefully, become better than any single one of them. Adversarial methods add a cool competitive twist. They set up a little game with 3 players, the teacher, the student, and a discriminator that acts like a referee. The student's job is to generate outputs that are so similar to the teacher's that the discriminator can't tell them apart. This game-like pressure forces the student to become an incredibly good mimic. Okay, now for what I think is a total game changer: data-free distillation. What if you can't access the original training data because, it's private or proprietary? Well, this method solves that problem by having the teacher help create a brand new synthetic data set. The student then learns from that fake data, never once seeing the original. It's a massive breakthrough for data privacy. This table gives us a great little summary. We've talked about self-distillation, where the model teaches itself, and multi-teacher, which learns from a group. We covered the adversarial methods that use that discriminator and the data-free methods that are huge for privacy. You can also see contrastive distillation here, which is another powerful technique that focuses on aligning the structure of knowledge between models. Each one of these offers a unique solution. It just shows how diverse this field has become. So let's connect all this theory to the real world. How is all this stuff actually being used today for the massive language and image models that are always in the headlines? Well, knowledge distillation is, and I'm not exaggerating here, probably the most important technique driving the entire open source AI movement. It is the main way that the incredible, almost magical abilities of giant closed models like GPT-4 get transferred into smaller open source models that anybody can download and run. And one of the most powerful ways it's being used is to distill not just answers, but the actual reasoning process. So you ask a large teacher model to show its work, to generate a step-by-step rationale for its answer. Then you train the smaller student model on that entire chain of thought. The result is amazing. You get a student that doesn't just parrot facts, it actually learns how to think. So as we've seen, knowledge distillation has evolved so far beyond just a simple compression trick. It's now a fundamental tool for transferring knowledge, for shaping it, and for democratizing the most advanced capabilities in all of artificial intelligence. And this all leaves us with a fascinating and, frankly, a profoundly complex question for the future. As this tech becomes more and more widespread, it's pushing us into a whole new legal and ethical frontier. I mean, if a student model's intelligence is derived entirely from a proprietary teacher, who really owns that knowledge? That is a question we're all going to be grappling with as this technology continues to shape our world.